Hey, this is a little bit more electrochemistry. I'll make this fairly short. Sorry, the last video was long. Had this reaction before. I remember copper is being oxidized. It's losing electrons. And it's giving those electrons to silver. Silver is being reduced. So remember, this is your cathode. This would be your anode, where oxidation is occurring. Cathode or reduction is occurring. Red cat and anox. One thing that I didn't talk about is this cell line diagram. Okay, cell line diagram, which actually I have kind of labeled wrong here. It actually, you put your anode compartment, cathode compartment, cathode. So in this case, our anode would have been the solid copper. You put a little line between it. It's in a solution of copper plus 2 ions. You put a double line. I don't know why I'm drawing them sideways. Usually they're up and down, straight up and down. Your silver ions and your silver. So this is your anode. This is your cathode always when you do this. Okay, when you actually draw a cell, you can draw them on either side, but in this line notation, you always know this is your anode where oxidation is occurring, and this is your cathode here. I call it an ion sandwich because the ions are in the middle, so an ion sandwich goes in the middle. All right. Remember, electrons flow from the anode to the cathode. Fat cat. From the anode to the cathode always. All right, I'm going to go on here a little bit. Let's talk a little bit about figuring out how to do a cell voltage. Okay, so if we have this reaction going here, first of all, you got to figure out what is oxidized, what is reduced. Well, copper is going from a +2 down to a 0, so that's being reduced. And zinc is being oxidized. So you get your little reduction table. Okay, get your reduction table, and we're going to figure out the overall voltage of this cell. And the cell voltage, electric potential is this, equals the reduction potential plus the oxidation potential. So remember, this is always showing reduction potentials. If we flip the reaction around, it flips the sign and is now an oxidation potential. So things that have a positive reduction potential are good at being reduced. Things that are negative are good at being oxidized. So for this one, if we look on our sheet here, copper +2 electrons going to solid copper. That reduction potential, maybe I've got that written down, so I have to look it up. I'll find it down here. I think it's 0.34 if I remember right. It is 0.34. So its reduction potential is a positive 0.34 volts. Zinc is being oxidized, so I got to take the opposite reaction that's on here. And zinc's reduction potential is negative 0.76. So if we say, okay, now we have zinc going to zinc +2 being oxidized. I don't usually put the electrons on here. So it is a negative 0.76 on here, so we flip that because it's now oxidation, positive 0.76 volts. So the overall potential of the cell is those added together. 0.34 plus 0.76, which would be 1.1 volts. That is the potential of that cell. Remember, the higher the voltage, the more current that cell can produce, more movement of electrons. If you look at letter B here, notice this is reduction. Iron just being reduced to iron +2. So these are, excuse me, this cell would have 2 aqueous things in it though. Okay, you'd have to use an electrode, some kind of metal as an electrode. Like usually we use platinum, gold works as well. Anything that takes electricity through it and doesn't react. So let's figure out this reduction potential. Iron +3 to iron +2 is a negative 0.03. Nope, sorry, that's not it. There's several ions on here, by the way. Positive 0.77. So this reduction potential is a positive 0.77 volts. This reduction potential is what we just had, which was a positive 0.34 volts. So if we're going to make a cell out of this, make a battery out of this, galvanic or voltaic cell, one thing has to be oxidized, one has to be reduced. Well, if we made this oxidation, that'd be a negative 0.77. Our overall cell potential cannot be negative. That'd mean it was not a spontaneous process that was happening, and it has to be spontaneous. So we need a positive cell potential. So we're going to flip this one and make it oxidation. So we're going to have copper going to copper plus 2, and that means that would now be an oxidation potential, and it would now be negative 0.34 volts. So our overall reaction would be Fe plus 3 plus solid copper, making Fe plus 2 plus copper plus 2. So really, if we think about what's happening here, there's a couple electrons being transferred. You actually would have to have 2 of those for it to be balanced. And then our cell potential would be 0.77 plus a negative 0.34 would be positive 0.43. Again, it has to be a positive cell potential for it to be a spontaneous process that's happening. All right. One thing. The potential of the cell is not changed by the coefficients in the equation. Okay, so that does not matter. The number of electrons being transferred does not change that. It's already taken into account by figuring out by these numbers. And that is positive for a spontaneous reaction. All right. Let's go here. I'm going to want you to make this cell. Notice platinum is in it. That is one of the electrodes. You also have 2 solutions here. That means that you have chromium here with a plus 3 charge, chromium here with a plus 2 charge. It must be being oxidized or reduced from plus 3 to plus 2 or plus 2 to plus 3. You can figure that out, which things can be oxidized, which can be reduced on that. So you're going to end up making that cell. I'm going to do one example. I'm going to do a cell. Here's usually what I'd give you. All right, so here's some information. So let's say you're given some solid magnesium, some 1 molar magnesium nitrate, 1 molar copper nitrate, some solid copper, KNO3, which will be our salt bridge. And we're going to make a voltaic cell. Okay, we're going to make a cell that works. So we'll figure out the equation, figure out the potential of the cell, label the anode and cathode, tell what reaction is happening at each, show the flow of electrons, and show movement of all ions. Okay. So we have here, 1 second. So if you remember, I gave you some copper and some magnesium. First thing I need to figure out is the reduction potentials of those. So let's look up copper, its reduction potential, which we've done several times now, is a positive 0.34 volts. And magnesium, its reduction potential is a negative 2.37 volts. So if we want this to work, we're going to make this oxidized, keep that as reduced. So let's flip this around. Magnesium to magnesium plus 2. This is now an oxidation potential. It's being oxidized. It's losing electrons. And this is now a positive value. So our equation is going to be copper plus 2 plus magnesium, making solid copper plus Mg plus 2. And if we think about flow of electrons are going from there to there. Magnesium's losing 2 electrons, becoming plus 2, meaning it's dissolving. And copper plus 2 is gaining 2 electrons, being reduced. And our cell potential would be those 2 added together. So what is that? 2.71 volts as our cell potential. If we draw the cell, okay, try to do the best I can of that. So there's a beaker. Here is my I'll put the piece of copper in one of them, magnesium in one of them. So it doesn't matter which one you make which, okay? It doesn't matter which one's the anode, which one's the cathode. So I'm gonna put my piece of copper there, piece of magnesium here. That means my solution of magnesium nitrate is here. So there's some magnesium ions floating around in solution over here. Over here then, make a blue since copper blue. Over here we have copper plus 2 ions floating around in solution. All right, these would be connected. I'm gonna get rid of this. These would be connected by a wire, maybe a voltmeter in the middle. It would be reading whatever we had, 2.71 volts once this is going. Again, a battery, we need a flow of electrons from one to the other. As long as there's any potential difference, there'll be a flow of electrons through the wire. We can light a light bulb, we can run a calculator, we can do whatever we need to use that battery for. So if we think, you remember our electrons, our copper is being reduced. Our copper plus 2 is being reduced. So reduction is happening here. That means this is our cathode, red cat, and oxidation is happening over here. That means this is our anode. Electrons flow from the anode to the cathode. So electrons are flowing this direction. So if we think about that, electrons are flowing in through this piece of metal into this solution. Every time a copper plus 2 gains 2 electrons, it forms more solid copper. So we're getting less and less copper ions in here and more solid copper. As we lose positive charge here, that means our salt bridge has to come into effect. So our KNO3, so K plus ions and our NO3 negative ions are in here. Well, the NO3 negatives, so we're losing positives here, so these Ks are going to go over there and replace it. Otherwise, we'll build up a bunch of charge and electrons won't flow towards that spot where there's a bunch of negative charge. Over here, as electrons leave, so again, electrons are leaving. As they leave, a different color. As electrons leave, we're getting more and more magnesium ions. So this anode is actually getting smaller. Okay? Magnesiums are turning into magnesium plus 2. So as this positive charge builds up, electrons won't want to leave. So we've got to equal out the charge by having some NO3 negatives go in there to equal out that charge. All right. There's your batteries.